tell you what, folks. Okay, I got an idea. Because you guys have been a little squirrely lately. No talking, all right? You were bad last Monday. What if I could do this whole thing with not blindfolded, but no notes? Who wants my notes? Ladies first.
Why?
Okay, here's the deal. I will nail this with no equations whatsoever. You have a cheat sheet, my cheat sheet, your cheat sheet. I will do this, and you don't need to take notes because you have them.
Can I keep it?
But you have
Is it mine to keep?
Yes, but
Okay.
you have to watch me. You have to make sure I don't get anything wrong. If I get anything wrong, it's off the test. Sound good?
Good.
Okay.
Mariana,
What do you think?
super critical. I like this.
What are the odds I'm going to get anything wrong?
I think there's a 5% chance.
All right, everyone. So I'm gonna do this now. If I'm
For every typo, do we get an extra point?
well, I've already told you what I'm gonna do. Okay, now what I want you to do, is, if I may forget something. Like, oh, you forgot delta S, right? That doesn't count, right? Let me, if I forget something, just remind me. All right, just remind me, then let's see if I can do it. If I completely fail, then it's off the test. Question?
Yes.
You gotta hurry.
Is the Maxwell equation?
Oh, you son. Yes, the Maxwell equations are on the cheat sheet. Okay, everyone, let's go ahead and get started because I will barely be able to do this. What inspired you to do that? Anyway, okay, kind of funny. Okay, now again, just keep track of me. All right, call me out if I make a mistake, and then it's off the test, and call me out if I just forget like delta S total or something.
Okay.
Okay, magic cylinder. Now I'm going to do all this with magic cylinder, but then I'm going to inject a couple of other type of questions, like an occasional derivation in the process as well. Okay, so while there are only 2 calculator questions, I'm gonna do this. I'm going to write equations with words, which will then do the other explaining words questions, because those are the same thing. So isothermal reversible obviously means that delta T is 0, K. When I have one of the 2 hard, the last section is 2 hard questions. One's derivational, one's calculator. And the calculation question is, give me H, A, U, A, G for a blah, blah, blah. I have like delta T on there. So that's a free point if I do something like that, which I did. Okay, now U per mole is 1/2 RT times degrees of freedom. So again, you see how test 1 comes up into test 2, and again, it can't be helped. Okay, I'm putting a star by that because that's really important. And all right, now what I get from that is that if the only way that you can change is if temperature changes. And so what I see from that, now I have that in mind. Changing U per mole is 0 if delta T is 0, right? Because 1/2 doesn't change with temperature, R doesn't change with temperature. Degrees of freedom, actually, they kind of do change with temperature. We'll get to that in a minute. But for the most part, for perfect gases, so this is a perfect gas result. And I'll make it clear whether I'm asking a perfect gas question or not. Perfect gas, that's 0. Okay, so I'm already well on my way to doing this. Actually, I'd like to do delta H next, and remember your Legendre transforms, because I may have that cat beds and barking dog question, may have made it back.
Professor?
Delta UPV.
What delta U 0
Delta H.
Delta U.
No, delta H is equal to delta H. I was testing you.
So this one's not on the exam, right?
No. Delta H is delta H. Hold on. Okay. Now there's one thing that is kind of tricky with this. That is tricky with some of these. And again, I do have a non-perfect gas question. I will show you a little bit more how to do that when I get to it. Okay, so we know that delta U is 0, and again, this one is a bit tricky. Knowing to substitute PV with nRT, it's a trick because otherwise this ends up being PdV plus VdP, and that can be done, but it's a pain in the ass. But this is also 0 joules, 0 joules. Okay, so U and H are 0. Now here's an example. I know that it's tempting to memorize that delta U and delta H are 0 and isothermal. It's not a lot to remember, but if you can just remember this, you derive the other two, right, without necessarily memorizing it. It's just an example, not that it's that hard to memorize that. Okay, okay, then work, delta U is delta W plus delta Q, and therefore delta Q is just minus delta work. Okay, oh, I haven't done work yet. All right, so work, again, I look at the cheat sheet, and I remember that. Now, I also remember, well, this is on the cheat sheet, but I'm going to put a little star by this anyway. And I also have to put a star by the fact that the exterior pressure is equal, the interior pressure is equal to the exterior pressure in reversible, and that's like by definition. Remember that was our earliest definition for reversible, was interior max exterior. But what I hope you see now is that instead of like suddenly pushing on the piston, if I match exterior to interior, what I'm doing is I'm very slowly pushing on the piston. By definition, I would be infinitely slowly pushing on the piston, meaning that really nothing's happening. That's why the other definition of reversible is equilibrium. Really nothing's happening. So reversibility is like this ideal that doesn't really exist, but it sure does make doing these calculations easy. Okay, so that means that this is minus PdV. Okay, now again, I'm using good calc, so I'm going to integrate it, and minus nRT dV over V, and I've got my, I actually have this on the cheat sheet. I have this spelled out on the cheat sheet, but anyway. I just like to walk through it. I like to know it. If I know it, even if it's on the cheat sheet, if you don't know it, you're not going to find it. I guess that's one way to put it. So I hope you know it, and then you see it on the cheat sheet, and then you're like, yeah, okay, that has to be the right equation. I know this is true, and it's on the cheat sheet. I know this. I got it right, and you do. Okay, and then that gives me delta Q as well. Okay, now that's all kind of test one stuff. Then we got into entropy. Yeah, entropy, right? I don't think there's anything else. Did I miss anything? Yeah, okay, so entropy. I did put, let me do a little bit of an aside here. I actually don't have this on there. But remember that I do have the definition of entropy itself as KLM number of microstates. And so I do have a little cheeky question like, you know, how many cats can fit in, 3 cats in 3 houses or 3 cats in 1 house? That's kind of how the question reads, or you figure out which one has the maximum entropy. I hope you remember that. Things like my reaction of one thing turns to 2 things, it's entropically favored. But if you actually have too many things, then it can actually be not favored because all the space gets taken up. That was the chess question. That did make it to the test. Anyway, that's a little bit of an aside, so but that is on there. Okay, when it comes to delta S questions, okay, I got to remember the question.
Yeah, you said that would does that mean the delta Q will be passive, like NRT and
Wait, what?
Delta Q?
Uh-huh.
So if you substitute that into that equation.
There's plus NRTLN.
Okay.
Yes, right, yeah. Just put a minus sign. Minus, I'm actually fine with that. If you're doing negative work, then that'd be expansion. Okay. Okay, now I do remember this, again, not that it's on the cheat sheet, and since we're reversible, let me integrate it. What I've got is minus delta work rev over T, and speaking like what we were just talking about, that it ends up being NRLN BF over DI. Okay, again, on the cheat sheet, but again, I hope you know it. And okay, then remember that this is system because I didn't say it was anything else. Just assume that means system. Now the total is equal to the system plus the exterior. And there's multiple ways to go about this, but reversibility does mean that it's 0 joules per K. And let's put a star by that. And now there's a couple ways to do that. In the book, I actually count up the system, which I just did, and I showed the exterior, why it's minus that. I guess that's my point. The exterior is minus the system. And that assures that the total entropy is 0. And there you go. Because again, when I have one of the last questions is a derivation, and then it's a gas expands, gas contracts, give me all of the S's, give me A, give me U, H. Anyway, so you gotta have that one down. Again, not that this is particularly difficult to remember. Okay, what have I got? A and G?
I have a question real quick. Where does the negative go in the delta work reversible? Yeah, where does that?
Right.
No, below. Yeah, where does the negative go into the next?
It's because you have negative NRT ln. So
Yeah,
it just
work
makes it
is
positive.
minus NRT. So I multiply by minus T.
Okay, thank you.
Right, there you go. Okay. Okay, now G. Let me do A. A is a little easier. A is U minus TS. Now, I never really ask A. I'm going to ask for the change in A, change in U minus the change in TS, which I've already covered is 0, but I'm going to write it out anyway. TDS minus SDT. Okay, we're isothermal, so that's, and that's also 0 isothermal. So this is minus TDS. Okay, which, when we integrate it, what we have is, and again, if you slip up on your calc symbology, I won't go donkey nuts on you. Okay, minus T delta S. Oddly enough, that's minus nRT ln VF over VI, which is reversible work. Okay. Let's see, and let me just point out that delta G is delta H minus delta TS. Okay, since H is 0, you're going to get the same thing, reversible work. I won't work it because it's the exact same thing. It's going to turn into TDS minus TDS minus SDT. Again, there's no delta T, so it turns into minus TDS, so that's reversible work. Okay, so there isn't much to say there. Let's see, have I done all the thermo? And then I think I do some derivations. Did I talk about entropy? I talked a little bit more about entropy, right, in my notes? Yeah, okay, so entropy did make it to this thing in a big, big way. Now, if you're not keeping up on notes, remember I'll post the video. I'll start on this as soon as it'll be late tonight, early tomorrow before the video gets posted because I have class myself. Okay, now entropy, the third law, entropy is a big, big, big part of this test because that's where we broke between test 1 and test 2. And remember the third law states, don't worry about residual entropy, that a perfect crystal at 0 degrees Kelvin has no entropy. And what that ends up allowing us to do is calculate the total entropy at some other temperature, which we will make it, let's make it the standard temperature, 298. That's not on the test though. Okay, so we take the entropy at 0 K, and we know what that is, and we add the change in entropy. And having a starting point, and then adding the change to that starting point doesn't give us the change, it gives us the total, right? So that's why this is special. Okay, and now I got to think about this. It's now practically, I know that the equations for the magic cylinder are CV dt, but practically you don't do these measurements in the magic cylinder. Remember that when we got into the third law, we started worrying about actual chemical reactions. And practically, we need to think of those as constant temperature and pressure. Magic cylinder is basically gone at this point. Just to remind you that, and of course I have to integrate this. I would integrate this from 0 K and probably to the melting point. Let's say that we're doing what is naturally a gas. Okay, so I need to let it melt. And then here's where you get jumps. in a graph of entropy versus temperature, because then you have to input energy to let it melt, but the temperature doesn't change. So it certainly makes it easy, but that's why when you look at an entropy versus temperature graph, now I told you a little bit about how it rises as a cube, but don't worry about that, that's not on the exam. We'll cover that in 346. Okay, so we get a jump. Okay, that's because it melted, and then we just keep going from the fusion temperature. Okay, so it's a liquid, so then it vaporizes, and there you go. Okay, so it's, sorry, it's a solid, it's a liquid. All right, wait, sorry, so this is here, this is here, this is here. Okay, but then of course the liquid will vaporize, and then it keeps going. I won't include that, it's all the same stuff, so on and on and on. Again, so remember that. Now I also had a question on homework comparing, the one you just turned in, comparing cyclohexane, which I got the formula wrong, sorry. But of course the keys there were to understand that because of these jumps, gases are always going to have more entropy than liquid. Remember that something with a higher heat capacity will probably have a higher entropy than something in the same phase with a lower heat capacity because of this. So anyway, it's not terrible. I think that the questions based on this are some of the easier ones.
Professor, without using a graph, why would you say a gas has more entropy than a liquid?
Because you can't just automatically assume that. It's just that when you're doing this for a gas, let's say that if you're doing a liquid, this integral goes to 298 and you haven't hit the gas phase because it's a liquid. Now, if it's a gas, you're going to not only go to the vaporization temperature, you're going to end up adding in this term. And this tends to be kind of big. Right? It tends to take a lot of energy. So it is kind of almost impossible for a vapor not to have a greater entropy than a liquid. But I don't know that's true of all liquids and all gases, because that's an infinitely large number of chemicals that are gases and liquids. Well, not infinitely, but anyway, you get my point. So you can make a reasonable assumption about what has more entropy than not. And it's really just a matter of looking at this equation and seeing, like what I just described, essentially. It's not terrible. This is the easier question. It comes early. All right, anyway. All right, now I also have a derivational question. Do I have that here?
Yes, for the non-perfect gas.
Okay, yeah, so non-perfect gas. I did, so as I promised you, I'm going to tell you way more because I feel like I've been, what did the person say, rude? And anyway, I know things have been funky, I've been a little overworked lately. So I do want to have a real gas derivation. So I have the harder questions, a real gas derivation. And so let's talk about du, what did I do, du dv?
dV.
Right, I want you to have the same, I could do anything, but, okay, so constant temperature, as I just said a second ago, magic cylinder, perfect gas, 0, but it's not quite 0. It's not quite 0 for a real gas. It's really close to 0. Now I know that this like, you gotta compartmentalize that. I hate to tell you, like, this is always true, except when it's not, right? Because that doesn't make sense. But that's what I did. Okay, now remember that you should be able to know what the change in U is, minus PdV, and heat is SdT. Okay, you should be able to do that. I think that's on the cheat sheet. You should be able to derive the others from there, including DH is that's the one that's all positive. Change in A is all negative. I got that wrong, I know. Good thing I didn't turn around, because you would have had me. Hold on, let me look at this. TDS, TDS, SDT, and G is the one that's mixed. So I remember H is all positive, A is all negative, and now it's, a little thing, that don't you memorize it, just derive it. It's just, I've been doing this 15 years, so I do have some, I mean, I do this for a living, okay, so it's easy for me to memorize this, but I want you to try that. Okay, do I get this right? Oh, anyway, okay, so you should be able to derive that, but now back to task, because this, as I already mentioned, is something I put on the test. So you write du, not what's on the test, by the way, I'm not doing the test question, big surprise there. You divide the partials by the partials. If you don't know that at this point, that's kind of mega bad. Okay, so it's true, that'd be mega bad. And you can see what you got is minus p plus t ds dv. Okay, now you can imagine I've given you a real gas equation, and I will do van der Waals, although I do something actually simpler than the van der Waals on the exam, because I want this to be slightly easier, and so I did. That's what I did, all right? Now I'm also going to have to know at this point that I need to look at the cheat sheet. Now here's how. I'm asking for this. When I'm asking for this, like maybe I'm asking does it go up or down? This is not the proper answer, because while this can be shown, this is something, right? It's going to be a heat capacity, it's going to be something that's either positive or negative, I know that, but you haven't shown it yet. I mean, technically, this can be positive or negative, you haven't proved to me yet, in my opinion, all right, so. Okay, now, then I look at the Maxwell equations. All the Maxwell equations are on the cheat sheet. I know I just put them on there, but I happen to know that I want the one based on A. It just turns out that it's the lower, the letters on the bottom are the ones that tell you which Maxwell equation you're looking for. I'm just making it easy. Don't memorize that, just find it. But maybe you might remember that. SDT minus PDD. And then I remember my trick. Now, if I ask you to do a Maxwell equation on the exam, I want you to write down the Euler test so that you know where it came from. But, okay, there's a trick. I keep saying don't memorize tricks, but this is such a good trick. The SDV at constant t, right? There's a minus, the SDV at constant t, dp dt at constant v. Minus, minus, and so that's plus. So what I end up with is minus p plus t dp dt at constant t. Now you can see why for a perfect gas this turns to 0, because it turns out that when you put in the perfect gas law, dp dt is p over t. It just turns out to be that way. I think that's just happenstance. So when I can already see for a perfect gas, I'm going to get minus p plus p. Okay, but what you're going to get, let me do t dp dt. T dp, okay, this isn't hard. The derivative of this is nr over v minus mv. And then there's no t there. So you see, I did this one because it's actually easy, right? Minus p. Okay, is that the answer?
No.
Why not?
Hold on a second.
Because what? Because I forgot to do what? Plug in the equation of state. Right. Minus nRT over v minus nb plus a n squared over v squared.
And that's B, right?
Equals a n, v. Okay. So I do something nasty like that to you, I'll just take off a point, because I'm not that much of a nasty. All right? So there you go, look out for that. Is that, did I forget anything?
No, not there.
Oh, there, okay. All right, folks. That is actually most of what I wanted to cover. So the rest of this is actually kind of easy. Let's do isothermal, irreversible, and there's not much to say there. Adiabatic, we'll use the rest of our time. Adiabatic reversible, isothermal, irreversible. Okay, now for all the reasons that I already covered, I don't want to kill a bunch of time just talking about the same thing I just did. The state functions, if they were 0 before, they better be 0 now because they're path independent. And recall, this is a test 1 thing. The paths, the reversible and irreversibility are technically paths. Okay, so those can't change. That makes sense. Let's see. Now, it is still true that the heat will be minus whatever I get for work. Okay, and remember that this ends up being easy. Almost. Okay. So actually, here, let me explain this better. Okay, change in work is minus exterior, just in case. I know this is kind of a test 1 thing. It actually is a test 1 thing. Now, the difference between reversible and irreversible is that if the exterior pressure is constant, God, I know it seems like ages ago, that the definition of irreversibility was expansion or compression against constant pressure versus nRT over V. That was our definition. What that means is that that part comes out of the integral, and as I mentioned, it ends up being very easy. Right, so throw a dog a bone. All right, and then of course heat is minus that, and that's how you keep the internal energy at 0. Let's see, now what have I got to do?
Entropy.
S? Do S, okay. Now, change in S is reversible heat, which is still minus reversible work, so this is still nR ln dF over dI. Okay, you can imagine I'm going to ask a question where I say, here's reversible, and here's a gas expands, a gas contracts, reversible, now do it irreversible, and I'm going to try to trap you. Some of them are different, some of them are not. Depends whether they're state functions in path independent, or if there are indefinite, remember that word, indefinite partials, indefinite differentials, and they are path dependent. Okay, no matter what the equation for the change in entropy is the same. All right, now there's not much left. I mean, again, I've actually kind of covered most of this. The total entropy is the change in the system plus the change in the exterior. Okay, by definition, not greater than, equal to, greater than. Not greater than, equal to, greater than. Equal to is reversible. If I put a little greater than equal to, then I'm saying that's reversible and irreversible, but this is irreversible. Okay. Now that means that, now again, this is well defined, but yeah, now this is the one that's funky. If I do this, you say that total entropy is simply greater than 0. That's all you know. And that's why this has always been unsatisfying to me, but at the same time, if you got this down, now this would get a little star. You got to remember that irreversible technically means total entropy increases. And that means that the exterior, which would be asked, is simply greater than minus the system. And there's really no other way to put that. And if the graders pay attention to me, if you just wrote that, I would give you full credit. It'd be a little bit easier to put the number down, because again, this is a calculated question. This is on the calculator question. And, okay, A and G. Again, I'm not going to go through the work. It's still minus TdS, which is still reversible. It's still reversible work. And here I'll write it just oppose against the F over D. I had to think about it for a second. So, all right. So notice that reversible work is still calculated in the irreversible. It goes to A and G. Remember that A is German for Arbeit, which means work, and this is exactly why. Now, here's another clue. When you're looking at equations and you're having a little trouble, because the cheat sheet's pretty full now, by the way, there's a T here. All right, that means constant temperature. I can't have a T in an adiabatic. I'm about to do adiabatic. I can't have a T in an adiabatic. It can't exist in that form because there's no one T. There's a final and an initial. If I have a letter T, then that means there's only one T. That means that this is isothermal. Or is that all
So
I
for
have here?
irreversible, isothermal, delta G and delta A is still equal to reversible work?
Yes, right. So you still calculate, so you're always going to calculate reversible work no matter what, if that's on the test, which I already told you this. Why did I just say that? So there you go. And so this might be the kind of thing, I know that might get you, so I might kind of push you in that direction, right? So it shows whether you're paying attention, which is what tests are for. Am I done on adiabatic? Isothermal reversible. Okay, adiabatic reversible. And this is going to take us the rest of the time because this is interesting.
And you said you wouldn't give an adiabatic irreversible, correct?
Let's just go over everything. Adiabatic reversible. Okay, now again, I try to keep the things you got to remember down to a minimum, but you got to remember that this is wrapped in glass wool. This is thermally insulated, so I might just say, hey, a thermally insulated transition, and that means there could be no heat exchange. Okay, so one of the few things, you want to remember this one. Okay, so delta Q is 0. Now that means that everything comes down to calculating change in temperature. Now you don't really have to memorize that. You're going to find that no matter what. You don't have a choice. You can't progress further from here unless you calculate the change in temperature. Okay. Now normally I got to start with U or work or heat. I've got heat. I've got now the change in U is the change in work, but I'm stuck. Okay, well hold on. So let me go for U then. Change in U is minus P PdV, okay, because I am reversible. Okay, again, I've used interior pressure for exterior pressure. Okay, now if I recall that little diagram, I'm kind of out of time. I do recall this. I recall that you can think of U as occurring in 2 steps. One where there's a volume change at constant temperature, and another one there's a temperature change at constant volume. So these have to be equal to each other. Now what you get from this is that derivation, which is really not too hard. dF over VI, VI is, now I always remember that this gets, these get reversed, and that's because of that minus sign, by the way. And I may, even if this is VI over VF and that's TF over TI, it's still to the CV over NR. Got it right? Okay. Okay, now what this does is it gives you delta T. TF. It gives you TF. And now you have delta T. I give you TI as part of the question. I have to. I mean, I can't not give you enough to answer the question. That's ridiculous. So now I've got TF. Okay, and then I got, I'm not using proper symbology. Then I've got CV delta T, which is the change in U, which is the change in work. And I've already said the heat is 0. So there you go. All right, now what? Now what? Now what? Now what? I got to think. All right. Delta H. Delta H is delta U plus delta PV, but this always seems to work. CV delta T. Again, PV equals nRT, so I just substitute nR delta T, and this ends up being CV plus nR delta T, which is CP. Now this is a perfect gas result, by the way. CV plus nR is true for perfect gas. Sorry, CV plus nR being equal to the heat capacity at constant pressure is for perfect gases. I know that when I did that derivation, this was a test 1 thing, I used the perfect gas law. But I'm going to stick with that on this test. It just gets a little overly complicated. All right, so that's delta H. I kind of have that one memorized at this point, but again, I've been doing it 15 years. Okay, the entropies get kind of interesting. So how did I do this? So this is one of the ones where you use entropy as a state function, and you find that there is a volume change. And again, I'm not doing the derivation for the sake of time. Yeah, I'm almost out of time. And I keep doing that, don't know why. There we go. So you can think of a volume change at constant temperature, and then at constant volume you change the temperature. Now what you do is, if you insert this thing here, what you get is 0. I did it in class, it's also in the textbook, but basically you can substitute VF, you can substitute Ti over Tf to the Cv over Nr into here, and the whole thing collapses to 0. So there is no system entropy change, adiabatic, reversible. Now, this is automatically true because there's no heat transaction, and therefore the total is also 0 joules per K. Okay, so remember, God, you just saw me work through this, but I swear to God, it is tempting to just try to remember all the entropies are 0, adiabatic, and reversible. Okay, that does work. It's not a lot to remember, but again, you know, I don't keep telling you don't do it, but then, God, that's easy. Anyway, so now, adiabatic irreversible is not too complicated, so what I want to do is take a little bit of time to do some more derivational stuff, because I want to get to, I'm not going to do A and G yet. I want to do a little bit of derivational stuff in this world, in this constant ds world. Adiabatic reversible means that ds is 0. And then remember that this leads to a whole host of derivations, which are nice because this is the world of equilibrium. Those others are not equilibrium. Adiabatic irreversible is by definition, anything irreversible is not equilibrium. Isothermal reversible is equilibrium, but there's still system entropy changing. So they're all different. This one is unique. Okay, so now what do I do with this? This is what I'm doing on my notes, right? Okay. Now, there was all kinds of, let me give you an easy one because I kind of have to be able to do this standing in front of here with no notes. I can, come on. All right, so what can I do? I can do dV, dt. Now, the thing is, what allowed me to write this is that I'm in the adiabatic reversible condition. And that means what I'm holding constant is entropy. So now remember I always said I can write dx dy at constant z, and I can make any of these up that I want to until I've applied a constraint. And I've applied a constraint. I'm only writing this down because I'm working with an equation that only comes about from the adiabatic equation, from invoking adiabatic reversible conditions. Okay, so there you go. Now, what can I do with that? What I could do is I could say, now don't forget too that I could do this. Okay, so I can ask you to describe that. All right, now P is always positive, CV is always positive, so this is always negative. Okay, so volume goes up, temperature what? Goes down. Right. So, adiabatic reversible. I'm thermally insulated. If volume goes up, gas is naturally cooled. And you get that from this. There you go. That's the thing I can do with this derivation. The other thing I could do is do this. Bring over the dV. Now, noting that P is nRT over V. What you would do with this? When you would do with this, you would actually end up back here. You would actually show that this is true. That's the kind of, fun things I can do derivationally with adiabatic reversible. Again, it's really unique. None of the others have all these little neat derivations and trickeries that I can do. And again, they are equilibrium systems. Equilibrium is kind of important, as you're going to see when we get back to class. That's how you calculate reaction yields, which will be next Monday. But now, if I want to apply this, if I'm doing adiabatic reversible, one of you was already asking, and I say, what's delta G? What's delta A, delta G? I'll do delta G. Now, you should be able to know that this is minus S dt plus dDP. And let's say that I ask for a GdV at constant S. Okay. So again, I'm trying to figure out how to calculate delta G if I ask an adiabatic reversible expression.
Irreversible?
So, reversible.
Irreversible?
No, reversible. Reversible.
Oh, I asked about adiabatic irreversible.
Oh, yeah, sure. Sorry. Anyway, Okay, so what I'm trying to do is calculate dGdV, and then I'm going to try to integrate it so that I can ask what's delta G in this condition. So I've already done dTdV. It's P over CV plus V. Okay, you know what? dPdV at constant S. Do you remember that one? That one was complicated. I think it was like, this was like minus V over P, CP over CV. I don't quite remember. It was complicated. No, the whole thing turns into a bloody mess. The whole thing turns into a bloody mess, and then when you try to integrate it, the problem is, look at this, entropy is a function of volume. Well, entropy is technically constant and adiabatic reversible, but you know what? This is just a mess. It really gets messy, especially if you do irreversible, which I'm going to do in 1 second. So dG and dA. Remember you had a dA on your homework? I'm not going to ask those. They're just too complicated. You actually would need a computer in many cases to solve them. Is that all I did for adiabatic? Adiabatic irreversible. You get delta T from, you calculate delta T from this, you know it's a horror show. The only thing to remember is that the total entropy is the exterior, which is still 0, plus the interior. And so that ends up being NR ln dF over VI plus CV ln TF over TI. There's not actually much to say here. Everything else is the same. What you're going to be able to do is fill this thing out based on solving this guy. You're going to get this, again, as always, delta T is key. Once you get delta T, you get work UH, and then you've got your final temperature. You have your initial, you can figure out your final volume, you have your initial. You calculate delta S from here. For your system, it's the same as the total. A and G are not on there, and that's it.
Just there is one thing. You said that the delta like the enthalpy, CP, delta T, it's an additional that you put over here.
Well, I did want to remind you, this actually didn't make it to, I don't think this is on the exam, but to remind you that, CV is change in U, CP would be the change in H. Yeah, there's that, and that was it? Okay. You ready? Ready? No. We're done.
When can we
You're fine. I nailed it.